All right, so we're going to look at some concepts here that underlie those fundamental processes. Why does something undergo beta emission, or why does something undergo positron emission? And that deals with nuclear stability. These nuclear reactions occur because of unstable nuclei. The more unstable it is, the faster the radioactive process occurs and the shorter the half-life of the reaction is. Nuclear density itself is very high. If you look at the density of a nucleus, ignoring the electron cloud, you're looking at something like 10 to the 14th grams per cubic centimeter. It's an incredibly dense, small, tiny spot. Strong forces are needed to hold all those protons together. If you look at something like uranium, which is the largest naturally occurring element, 92 protons being held together in one spot. They're equal charges. They're all positives. Pushed all together in a very tight, short, small amount of space, that's difficult to do, to hold all those protons together. Because they call it Coulombic repulsion. All the protons repel each other because they all have positive charges. So the result of this is that there's a pattern of stability in the elements, all of them, from hydrogen all the way up through as far as you want to go. And that pattern of stability looks something like what's on page 974 of your textbook. And so on the y-axis is the number of neutrons in the nucleus, and the x-axis is the number of protons in the nucleus. And there's a target ratio. That line that goes up through there, that band that goes up through there, that's the stable band, or relatively stable. The further you are away, either above or below that band, the less stable you become and the faster the nuclear decays start to occur. So some books will call that a band of stability. That's what this one uses. Some call it an island of stability in that sea of possibilities for neutron to protons. So it's all about the neutron to proton ratios. For small elements, it's about 1 to 1. So most of the small elements in the periodic table that you look at have an atomic number that's half of the mass number. So carbon has a mass of 12, atomic number 6. Nitrogen, 14 versus 7. Oxygen, 16 versus 8. The bigger the atom gets, the more neutrons it tends to accumulate. And the way I think about this is that it's the neutron's job to mediate all these positive charges. The more and more positive charges you put in to the nucleus, the harder it is to hold them together. Think about taking a couple of bar magnets and turn them around so both north poles are at each other and hold them there. You can do that. That's not a big deal. Now we put in another one, and another one, and another one, and another one. Put in 92 bar magnets and hold all their north ends together indefinitely. That's a tough job. That takes a lot of energy. So the bigger the atom gets, the more binding energy it needs to hold all of those protons together in the nucleus. Now to me, the way I think about it, this is just me, the way I think about it is the neutron's job is to mediate those positive charges. And it allows the positive charges to separate just a little bit so they're not touching each other, they're close to each other. And the neutrons, the more neutrons there are, the more it can mediate those processes. But we can't just put all kinds of neutrons in there. When we get too many neutrons, it also becomes unstable and leaves that line of stability that we talked about. So for the small elements, it's about 1 to 1, and then it starts to go up from there. So larger elements, tends to be greater than 1 to 1 in terms of the neutron count. So for uranium, we got several isotopes of uranium. 234, 232 probably exists. 234 is a common uranium isotope. 234 mass units and 92 protons. There's like a 1.5 neutron per proton ratio there. So that ratio does go up from 1 to 1 as you get larger and larger, especially after you get past about the end of the first row of transition elements. Then it really starts to deviate upwards after iron and nickel and zinc. That ratio tends to get larger and larger. So if we get away from these target ratios, 1 to 1 for the small ones and a little bit more than that for the larger ones, we start to see some of those processes occur. So things that are neutron rich. If an element is described as neutron rich, that means it has a mass number for that isotope that is greater than its mass number on the periodic table. So the isotope that we're looking at, mass is greater than molar mass. Atomic mass greater than the molar mass. That means there's more neutrons than the average flavor of that element is supposed to have. When that occurs, when they're neutron-rich elements tend to undergo beta emission. And the reason why they tend to undergo beta emission is because during the beta emission process, a neutron converts into a proton and an electron. So a neutron is converted into a proton, which allows this isotope to reapproach that island of stability. If a neutron if it's too high on that chart and a neutron converts into a proton, it moves closer to that line. If it's not stable enough yet, it might go through another one, until it gets to the stability line. So those are neutron-rich elements. Some of the elements are neutron poor. I said element again, I mean isotope. Some isotopes are neutron poor. That means that the isotope mass is greater than the molar mass on the periodic table for that element. So these are cases where the elements are below that line of stability. There aren't enough neutrons to make it stable. And these are candidates for positron emission or electron capture, because both those processes result in moving closer to that line of stability from the bottom side, moving up. In particular, positron emission has a proton converting into a neutron plus an electron. So we convert a proton into a neutron, that's going to raise it up in that table because now we have more neutrons relatively than protons in the original element. So we can use this as a predictor for what kind of decay cycle might be encountered by a particular isotope. So now we're going to look and assign electron-rich or electron-poor to some isotopes. A couple of them we might have seen before, but we're going to still do some predicting. So we got 11/6 carbon, and we've got 63/28 nickel, and we have 3/1 hydrogen. That's referred to as tritium, tri for 3. Tritium is hydrogen 3. And we also have 6/3 Li. So in each of these four, we're going to decide, is it electron rich or poor? And then guess what kind of decay it's going to undergo because of that. So when we look at carbon 11, isotope mass is 11. The molar mass of carbon on the periodic table is 12. So this mass is too low. So this is neutron poor. Things that are neutron poor tend to go through positron or electron capture. If I asked you this on an exam, I just want you to give me one of those. It would undergo positron emission or undergo electron capture. So that's what we're doing for the other three. Deciding if it's neutron rich or poor, and then deciding how does it decay and become more stable. So nickel 63. 63 compared to nickel on the periodic table, which is 58.7. So this is neutron rich. Its mass is much higher than its average mass. Things that are neutron rich tend to undergo beta decay. Now over here for hydrogen 3. 3 is much bigger than the regular 1 for hydrogen, so this is neutron rich. So we would expect this also to undergo beta decay. Lithium 6. In the periodic table, mass of lithium is about 7. So this has a lower mass, so this is neutron poor. So we would expect positron emission or electron capture, either one for those. Okay? So make sure you can work those out. Multiple choice questions write themselves, right? So assign whether it's got a mass that's too high or too low compared to the periodic table mass, and decide if it's neutron rich or poor because of that, and then decide which beta, which decay cycle it would likely follow, and go from there.